In this lesson, graphing square roots and cube roots, we are going to take a look at the different aspects of the graphs of each of these. So back in Unit 1 we talked about quadratics, and quadratics had also a parent function. The parent function in quadratic was just y equals x squared. That was the most basic of them. For a square root, the parent equation would be f of x equals just the square root of x. Now keep in mind, when we look at the graphs, we are not going to be looking at imaginary numbers, so we are only looking for our x values for our domain to be greater than 0. So we don't want anything inside of your square root to be a negative number. So for your domain, we can include 0 because the square root of 0 is just 0, which is possible. And then any other number greater than 0 would work inside of a square root. Now keep in mind, this is the domain and range of the graph of only the parent functions. We're going to be translating them here in just a minute. And the range, well, if 0 is the smallest x value we can have, and we plug 0 in, so 0 is the smallest, take the square root of 0, so the smallest y value is also 0. And that can be bigger than 0 as well. And then the graph of that, I'm just going to write a little sketch. The graph of a square root will look like that. It looks like half of a quadratic that's sitting on its side because we only have the positive square root of x. We don't have the negative square root of x. For a cube root, the parent equation would be f of x equals the cube root of x. Again, that's the most basic of all cube roots that we have. Now for the domain, remember that's all the values for x. So if you think about it, in the square root we had to eliminate, we couldn't have possible values for x in a square root because we didn't want negative numbers. But negative numbers are okay inside of a cube root because if you took the cube root of a negative 8, would just be a negative 2. So cube roots, you can include those negatives. In fact, you can include all real numbers, so negative infinity to infinity. And then the range, since we're including any x value, any y value is also included, so negative infinity to infinity. And the graph for a cubic function looks like a cubic function that's laying on its side, or yes, a cubic function that's laying on its side. So let's take a look at this graph. Graph y equals 1/2 the square root of x and y equals the square root of x on the same set of axes, and then compare the two graphs. And then we're going to find the domain and the range. So the first thing is that they are both square roots, so we get an idea of what they're going to look like. One thing that would be beneficial is to make a little table of values here to graph it. So this will be just for the parent graph, y equals the square root of x. So I'm going to choose some x values, so I'll choose 0. The square root of 0 is 0. I'll choose 1. The square root of 1 is 1. And when I'm choosing these values, I'm going to choose values that are perfect squares so that I can take the square root of them. So the next one would be 4. So the square root of 4 is 2. And then the last one I'll choose is 9. And the square root of 9 is 3. I'm going to go ahead and graph that on this graph on the right. And I'm going to use the same color that I just used in my table so that it's color coded. So we have 0, 0, 1, 1, 4, 2, and 9, 3. So that would be y equals the square root of x. And then I'm going to change colors here, and I'll do the 1/2 the square root of x. I'm still going to choose the same x values that I did in the previous one because they were nice, but we're just going to take half of the square root. So if I plug in 0, the square root of 0 is 0, and take half of that, you're still going to get 0. And then we have 1, the square root of 1 is 1, times 1/2 is just 1/2. And then 4, the square root of 4 is 2, 2 times 1/2 is 1. And then the square root of 9 is 3. 3 times 1/2 is just 3/2, which is 1.5. I'm going to try to zoom in a little bit to make it easier to graph. So 0, 0, and then 1/2, and then 4, 1, and 1.5. So as you can see, this 1/2, the square root of x, has collapsed and compressed closer to the x-axis. And the reason for that is the a value. If you think back to quadratics, we had an a value out in front. The a value determined if it was reflected. It determined if it was fatter or skinnier. Vertically stretched, compressed, that's the fatter, skinnier. So this 1/2 made it vertically shrank. It made it skinnier, if you will. So let's see. This is the comparison. It has a vertical shrink of 1/2. That was the y equals 1/2 square root of x. Let's see. They have what we call the same locator point, which we'll talk a little bit about later. The locator point essentially is just the vertex, quote unquote, the vertex where it's located around. In this case, the locator point would be 0, 0. It's this point here where the square root function it initiates from. And they're both square root functions. It's pretty much the comparison that you have there. And the domain, well, the domain for both of them is exactly the same. The furthest left point would be 0, and it includes 0. And then it goes to infinity. So we're going to include 0 and go to infinity. And then the range, the lowest point is also 0, and it's going to continue up. Again, very slowly it's going to continue up, but it will continue to go without a bound to infinity. The next graph is of your cube roots, and we have -3 times the cube root of x and the cube root of x. Again, the parent is going to be our first one, so I'm going to go ahead and make a table of values for that. So we'll choose 0, and this time I'm going to choose x values that are perfect cubes so I can take the cube root of them. So the cube root of 0 is just 0, and then 1 is the next perfect cube. The cube root of 1 is 1, and really the last one that will fit on our graph will be 8 as an x value, and the cube root of 8 is 2. So we'll graph that. So 0, 0, 1, 1, and 8, 2. Now remember, a cube root also goes in the other direction, so we're going to go ahead and choose some other points to add on to here. We can choose -1, because the cube root of -1 is -1. And we can choose -8, because the cube root of -8 is -2. So that gives me 2 other points that I can use on my graph to create that cube root graph. So that'll be y equals the cube root of x. And the next one that we have to graph is -3 times the cube root of x. Again, I'm going to choose the same values. Hopefully they will work out for us. So we can choose 0. So the cube root of 0 is 0, so I'm plugging it into this equation over here. And then I'm going to multiply the cube root of 0 times negative 3, which is just 0. And then the next one I'll choose is 1. The cube root of 1 is 1 times negative 3 is negative 3. And then I'll choose the 8. The cube root of 8 is 2. 2 times negative 3 is negative 6. And again, since I know I'm going to have to choose, I can choose negative 1 and negative 8. We'll do that as well while we're here. So let's see. The cube root of negative 1 is negative 1. Negative 1 times negative 3 is 3. And then the cube root of negative 8 is negative 2. Negative 2 times negative 3 is positive 6. So we're going to go over to the graph and graph those points. So now for this one, they're not exactly they don't look to be exactly the same shape. The reason that this one is looking a little bit different is because of the negative 3 in front. So the negative 3 did a few things. So one of the things that the negative 3 did was to make it vertically stretched, made it versus the last one, which was a shrink, because it made it closer to the x-axis. This one made it further away from the x-axis, so that one is vertically stretched. And that was because the number 3 is bigger than 1, versus the last one we had a number 1/2, which is less than 1. The negative also reflected it across the x-axis. So that's a few things that we want to note about this graph. So this one is y equals negative 3 cube root of x is vertically stretched by a factor of 3, and also it's reflected across the x-axis. And the domain and range for these are both the same. The domain for both of them is negative infinity to infinity, and the range also negative infinity to infinity. Now for the next one, let's see what we have. The period of a pendulum is the time the pendulum takes to complete one back-to-back, back and forth swing. The period t, which is in seconds, can be modeled by the equation that we see right here. T equals 1.11 times the square root of L, where L is the pendulum's length in feet. And it says use the graphing calculator to graph the model. And then we're going to use the graph to figure out how long the pendulum is with a period of 3 seconds. So if you haven't already done so, go ahead and get a graphing calculator, or you want to type this in to Desmos. There is no L in Desmos or on your graphing calculator, so you're going to have to use X, and then capital T would represent your dependent variable, which is your Y value. So the independent variable is L, and then T, which would represent your dependent variable. So here on the right, I went to Desmos and I took a screenshot of this graph, what it should look like. And over here, I plotted a point. I had to come really close to it in order to estimate it. Yours probably doesn't exactly have a 3, but just a few things that we should note about this graph itself. The x-axis would be the length of the pendulum. So the length of the pendulum is the independent variable because the period, which is your dependent variable, which is your y value, is dependent upon the length of the pendulum. So therefore, we talk about independent versus dependent. So in this case, the period depends on the length. So it's asking us how long the pendulum is with a period of 3 seconds. So I had to find where my y value is 3. And then looking at the graph, it's the x value, which is your length of your pendulum. And it was approximately 7.3 feet. In this key concept, we're going to talk about the translation of these radical functions, the square roots and cube roots. So step 1 is to make a sketch of its parent. So it'll be either a times the square root of x, or it'll be a cube root that you'll make a sketch of. And then step 2, you're going to translate the graph horizontally h units and vertically k units. And that'll be pretty similar to what we've done, and it's called the locator point, where we move things and how it moves around, and it's going to be identical to how it was in quadratics. So I'm going to do a couple examples down here at the bottom before we even go ahead and do a closer sketch of them. So for example, if you had y equals the square root of x minus 3 plus 2, the locator point, which I'm going to abbreviate as LP for locator point, would be 3, 2. Because remember, this is x minus h and then plus k, identical to how it was in quadratics. So for this square root one, you would move to 3, 2 on your x-axis, put a point, and then know that a square root would look like this. So another example of this would be y equals the square root of x plus 1 minus 3. The locator point in this one would be -1, -3. So when we graph that, you'll graph the point -1, -3, and we know a square root, what the general shape of the square root looks like. And then for the cube root, again, identical to the same process. So if you had y equals the cube root of x minus 4 plus 1, the locator point would be your h and your k again, which would be 4, 1. So we would go to 4, 1. And that is the point that was shifted from 0, 0. And a cube, the cube root looks like this. So you have your point of inflection. So at that locator point, right there, 4, 1, that's called the point of inflection. And that's just where it goes from concave up to concave down. So it looks, usually when I graph my cubic functions, I graph them, or my cube root, I graph them from the locator point to the right, and then I go back to the locator point and go to the left. So we can go ahead and actually graph these. So the first one I notice is a square root, and the square root, we know again what the general idea of what this is. So I'm going to list out the locator point. The locator point in this one would be 3, 2. And that's where I'm going to graph it for the first one. So 3, 2 is your locator point. So I know that that is going to be the start of my actual square root graph. Now a few things to note about the -2 in front. I know that this is going to be reflected across the x-axis because of the negative sign, and the 2 will vertically stretch it. It'll be further apart than the normal square root function. Now I'm going to plug in some numbers, and I'm going to use numbers that are will make this a perfect square inside. So I'm going to choose the number 4 for my first x value. So if I plug in a 4, I'll have 4 minus 3, which is 1. The square root of 1 is 1. Then 1 times negative 2 is negative 2. Negative 2 plus 2 is 0. So that was at 4, comma 0. So I plugged in a 4, and 0 was my output. The next x value I'm going to substitute in is 7, because when I do 7 minus 3 inside of here, I'll get a 4, which is a perfect square. So if the square root of 4 is 2, so I'll have negative 2 times 2 plus 2. So I'll have negative 4 plus 2, which is negative 2. So that should give us enough points to kind of give us a general idea of what this square root will look like. Now we know that it's actually a little bit different than what we've done with square roots. That's because of the negative sign reflected it across the x-axis. So, and then it is stretched out just a touch. So the domain for this one, the furthest left point, is this x value right here at the locator point, and that would be at 3. And it can include 3, there is a point there. And the furthest right point is infinity. And then the range, the lowest point, this is going to continue down slowly, but it's going to continue down. So the lowest range would be negative infinity for the y, or for the left. And then it's going to go all the way up to this highest point at the locator point, which happens to be at 2, which is, again, the locator point, the y value. For number 5, so we have a cube root in this one, so I want to choose values that are perfect cubes after I plug them into the x value. But we can at least find the locator point. The locator point on this one, that point of inflection, would be negative 4, comma negative 1. So right there in the third quadrant will be that point of inflection. And let's go ahead and choose some x values that would be good for us. So I'm going to choose negative 3 first. So negative 3 plus 4 is 1. The cube root of 1 is 1. 1 times 3 is 3. 3 minus 1 is 2. So negative 3, comma 2. And then we'll choose 4. So I could plug a 4 in here. 4 plus 4 is 8. The cube root of 8 is 2. So we'll have 3 times 2 minus 1. So 6 minus 1 is 5. And that was an x value of 4. So I know that that's the direction that part of the cubic is going to go in. And then I'll choose negative 5. So negative 5 plus 4 is negative 1. The cube root of negative 1 is negative 1. So we'll have negative 3 minus 1, which is negative 4. And then if I choose my next one, it's going to be off of the graph. So it'll look something like this. So for the domain and the range for this one, they are both the same. They're both negative infinity to infinity. So all real numbers for both domain and range. We have a few more. Number 6, another square root here. So this one has a 1/2 as your a value. So this one is going to be vertically shrunk. So it will be pretty close to the x-axis, pretty narrow, almost. It'll kind of look like a straight line when we graph it, but in fact it does curve. And then we have a square root, so we kind of get an idea of what that will look like. So the locator point for this one would be 3, negative 1. So that'll be your starting point. We'll choose 4 as your first x value. 4 minus 3 is 1. The square root of 1 is 1. 1 times 1/2 is 1/2. 1/2 minus 1 is negative 1/2. And then the next one would be, let's see, 7. 7 minus 3 is 4. The square root of 4 is 2. 2 times 1/2 is 1. 1 minus 1 is 0. So it'll curve just ever so slightly because of the 1/2 made it much narrower. The domain for this one, the furthest left is at that locator point, the x value. So the furthest left x value is -3. And then that continues to the right to infinity. And the range, the lowest point, is also at the locator point, and that happens to be at -1 for the y value. And that will also go to infinity. Again, these square roots, they look like they're just going to level out, but they do go up ever so slightly. So it may take a really long time, but it will go to infinity. And this last one, we have g of x equals negative cube root of x plus 2 minus 3. So our locator point for this one is -2, -3. Now, again, keep in mind that this one will be reflected because of the negative sign, but we won't have any kind of stretch factor, or we won't have any kind of, it won't be pretty narrow. It'll be the same as the parent graph as far as how tall it is. So let's go ahead and plot that locator point. So we have -2, -3. And then choose a couple values. So if I choose -1, -1 plus 2 is 1. The cube root of 1 is 1, but you have that negative, so that would be -1 minus 3, which is -4. And I'm going to also choose -3. -3 plus 2 is -1. The cube root of -1 is -1. Times a negative is a +1. Minus 3 is -2. And then we're going to choose 6. So 6 plus 2 is 8. The cube root of 8 is 2. Times a negative. So -2 minus 3 is -5. And then the last one would be -10. -10 plus 2 is -8. The cube root of -8 is -2. Times the negative makes it a +2. Minus 3 is -1. So starting at your locator point each time, it's a little bit easier to graph. So here we have our locator point, which is your point of inflection. So that's the point, again, where it changes concavity. The domain and the range, again, for this one, for both of them, -infinity to infinity. And there you have it.